0, or x minus 2 equals the opposite of 0, which is going to end up being the same thing. So x equals 2, and that's our answer, 2, 0. You could check this one, will solve that to the same thing. 2, 0, so 2, 0. There we go. So for this, I like to do 5 points as well, just like with the parabola. So let's make space for 3 other points. Okay, as usual, the values that I like to pick are 1 and -1. Let's do 1 and -1, and then 1 for y. Okay, let's block that off. Okay, so here we go. X equal to 1. Y equals absolute value, 1 minus 2. Y equals absolute value of -1. Y equals 1. Voila. Ooh, I just smeared my... Okay. 1, 1. Plot that point, 1, 1, right here. And I didn't even label that one. Naughty, naughty. Okay. All right, 2 more to go. Next one we have is x is -1. So y equals -1 minus 2. Wow, that's kind of interesting looking. Okay. Y equals absolute value of -3. Y equals 3. So plug that in. Then the point -1, 3. Let's see, -1, 3. 1, 2, 3. And then the y value of 1. So notice I pick positive and negatives for both of them, and 1 for x and 1 for y, to make sure that both my x and my y, I can test the same numbers for both of them. Alright, so testing out y equal to 1. So I have 1 equals the absolute value of x minus 2. Okay, when I split this one, it's going to be different. Let me go ahead and white out down here. I didn't plan the space very well. Okay, so splitting this to get it out of the absolute values, I get x minus 2 equals 1, or x minus 2 equals -1. Go ahead and solve. Add 2 to both sides. X equals 3. Add 2, add 2. X equals 1. Oh, I have 2 values here for x, which means I get 2 points. I have another instance where y is 1, and x this time, instead of being 3, is a -3. So the y value of 1 gave me 2 different coordinate points. Let's go ahead and plot those. So we have my y value of 1, and I get x value of 3. 1, 2, 3. 1, 3. And the x value of 1, -3. 1, -3. Where did I get -3 from? That should be 1, 1. Whoa! Sorry, that was very confusing. I confused myself. Okay, when we plugged in the y value of 1, we solved and got 3 as one of the answers. So that's where that 3 came from. And then when we plugged in 1 for y, we also got another answer, +1. So that should have been a 1. Okay, 1, 1, which is actually a point we already got. So do we have our 5 points? Yep, 1, 2, 3, 4, 5. We can go ahead and draw in the graph for the absolute values, which remember looks like that V shape. So it's important to put positive and negatives of both your x and y values so you can end up getting a good idea of the graph. And there we go, our absolute value. See the V shape? This has a different shape than the parabola because it goes, has that point, whereas a parabola, remember, should have the smooth curve. All right, now that took some time. Okay, so here we are, moving on. Intercepts, very important idea, the intercepts. And notice it says this holds true for all equations. So if you're working with parabola, lines, Any equation you can think of, when you're graphing the intercepts, this is how you always find them. If you want the x-intercept, you're going to make your y value equal to 0 and solve for x. Y-intercepts, you're going to set x equal to 0 and solve for y. So you might be asking, what's an x-intercept or a y-intercept? Okay, so should be something we've covered before, but if you need a refresher, it's time for the refresher. Okay, so if you have your coordinate plane and you have a graph, let's say your graph does this. Really weird. The x-intercepts are where your graph crosses the x-axis, which would be here, here, and here. So there would be 3 x-intercepts. Your y-intercepts would be where your graph crosses the y-axis, which would be once right there. Okay. So for example 5, it says find the intercepts for x equals x squared minus 2x minus 3. Okay, so 2 intercepts. Let's find the x-intercept, which means we're going to set y to 0. Let's do that. So setting y to 0, we have 0 equals x squared minus 2x minus 3. Ooh, that's a quadratic. Let's go ahead and factor that to solve for x. And using the 0 factor property, set each one to 0 and solve. X equals -1, x equals 3. Which means we actually have 2 x-intercepts. So we have one that's -1, 0, and 3, 0. Yeah, so that was the x-intercepts. Let's find the y-intercept. This is when we set x to 0 and solve. So rewriting my equation, set x to 0 and solve. So y is going to equal 0 squared is 0, minus 2 times 0, minus 0, minus 3. You don't need to write all those zeros down if you know that that all goes to 0. Just showing you what happens. Here's my line to indicate where my work goes. We have y equals -3. Okay, so that is my y-intercept number. There we go. That's my y-intercept and my x-intercept. So hopefully this was a bit of a refresher. If not, good thing to know now. Moving on, circles. Okay, so the standard form of a circle that has a center, hk, so for example, when you graph a circle, the center is right there, what you'd probably think of as the center of a circle. And the radius is r. So this thing right here, the radius would be r. And here's the equation that we have. X minus h squared plus y minus k squared equals r squared. If we get our equation into this form, we can pull off our center value and our radius. Let's take a look at example 6. Graph the circle. Okay, so the reason I know that this is the equation of a circle is I have my x squared and my y squared, and then I have an x to the 1 power, and you might have a y to the 1 power. Also, the number in front of the x and the y is the same. In this case, it's a positive 1. All right, so in order to graph the circle, I want to get this into center radius form, which means I'm going to need to complete the square. Okay, so here we go. Let's start. Okay, so plus 2x minus 8 equals 0. Now notice the form has our x value squared plus our y value squared. This looks similar to completing the square. So what I'm going to do is get my x values together, plus 2x, leave space for the perfect square number, plus, and my y values together, oh, there's only one. And then move the 8 to the other side. Same idea for the completing the square that we've done before. All right, so now I want to find the perfect square numbers that can make these look like a binomial squared. Okay, same idea, the same formula. We take b divided by 2 and square it. In this case, our b is a 2. So that squared is going to equal 1 squared, which is 1. So my perfect number is 1. Now this is interesting here. There is no b value. But technically, we can just be sneaky and rewrite this as y minus 0 squared and move that out. Okay. So you could check y minus 0 would be y, and then square that would be y squared. So it's a sneaky way of putting our answer, or our equation, sorry, into the right form. All right, let's go ahead. Factoring that, that's going to come out to x plus 1 squared plus y minus 0 squared equals 8. And there we go. My radius, or sorry, my center is going to be... Now the center is the opposite of the number in the middle. So what's the opposite of 1? Negative 1. What's the opposite of negative 0? Well, positive 0. We don't really have positive and negative 0, but let's go with that idea. And then our radius is r. But careful, notice, remember, the radius squared is this number. So radius squared is 8, but I don't want radius squared, I want r, which means I need to solve for r. So take the square root. R equals plus or minus the square root of 8. Simplified, r equals plus or minus 2 root 2. We don't have negative radiuses, those don't exist. So we're going to go ahead and take the positive. So the radius is 2 root 2. All right, let's go ahead and graph this. My center is negative 1, 0, negative 1, 0. And my radius is 2 squared of 2. Okay, that's kind of hard to graph, so I'm going to estimate the radius. Okay, so the radius was originally square root of 8. So the square root of 8, that is in between the square root of 9 and the square root of... What's another perfect square root? Square root of 9 is 3. The next perfect square root is square root of 4. Square root of 4 is 2. So I know that the square root of 8 is in between 2 and 3. So I'll just say square root of 8, we can roughly graph it as 2.5. Okay, we only do this estimating when we're graphing. We would not give our answer as 2.5. Our answer would be this. Sorry, I just crossed right through that. Okay, so for radius, we'll go up 2.5, 1, 2.5. To the right, 2.5, 1, 2.5. Down 2.5, 1, 2, 2.5. And to the left, 2.5. To the left, 1, 2, boop. And we'll go ahead and, this is going to look slightly hideous freehand. Forgive me, circles. I do not mean to offend you. Okay. Not too bad. Alrighty. So there we go. For graphing our circle, we did completing the square to get it into the form. And then from there, we can just pick off our center values, find r, and plot the center and your radius up, right, down, left. Here we go, symmetry of a graph. So the symmetry of a graph, what does that mean? Well, that means if you took something, let's see if I have a piece of, where'd my sticky notes go? If you had your graph, ooh, no, you're dying on me, don't die. Here is our axis. Let's see, can we see this through? Ooh, kind of. Let me make that darker. The jumbo pen. There are different ways for a graph to be symmetric. There are 3 ways. We have symmetric about the origin. So, symmetric about the origin would mean was if we had a point up here, x, y, there would be the opposite point down here, negative x, negative y. So an example of that would be, let me go ahead. Ooh, it does show up. Awesome. So this graph here, if I was to go ahead and flip it about the origin, it looks exactly the same as it did before. So that is symmetric about the origin. Okay. If I was to take this graph, though, Let me find another one. Here's a value here, so we have x negative y and negative x, y. So a value that would be symmetric about the x-axis, let's check. Here's a graph here. So if I took this and I flipped it about the x, so flip, if you can see it, that does not look like the same as it did before. So it is not symmetric about the x-axis. Okay, so that's checking for x. The y-axis, let's go ahead and try flip it about the y. Does that look the same as it did before? No. So this one is not symmetric about the y-axis. Let's check this. Is this symmetric about the origin? Let's go ahead and flip it. About the origin. Ah, it is symmetric about the origin. Looks exactly the same as it did before. Okay, so that's kind of the gist of what we're looking for when we're looking for symmetry. Is if we move the graph around across either the x-axis or the y-axis or the origin, does it still look the same? Like as if we hadn't touched it at all. So I'm going to go over the 3 tests. So we have the test for symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. 3 options. So how we test symmetry about the x-axis is we're going to make y be the negative and see if we get back the same equation. What does that mean? Well, I'll show you. So let's see, we're looking at our equation, x squared plus y squared equals 1. I'm going to make y a negative. And let's simplify this. Any quantity squared is going to be a positive, right? So that means this simplifies into that. And notice this is the exact same equation we started with. So our equation is symmetric about the x-axis. So is symmetric about the x-axis. All right, let's check symmetry about the y-axis. So this time it's different. We're going to make make x the negative and check to see if we get back the same equation. Let's go ahead and do that. So we start with x squared plus y squared equals 1, plugging in the negative value for x squared. Do we get back the same equation when we simplify? Let's see. Ooh, that's going to be x squared again. Any quantity that's negative squared will be positive. Plus y squared equals 1. Hey, we got back the same exact equation. Hence, this is also symmetric about the y-axis. Symmetric about the y-axis. Lastly, let's check the origin. We have to make, this time, we make x negative and the y value negative to check the origin. Okay, so 2 things. Both the x and the y are negative for checking about the origin. So here's our original equation. Let's plug in those values and see if we get back the same equation. Simplifying, well, anything negative squared is going to be itself. And once again, anything negative squared is going to be itself. And what do you know? We get back the exact same equation. So it is symmetric about the origin. So this equation is symmetric about the x-axis, y-axis, and the origin. And it actually makes sense because it is a circle. So let's see if that makes sense, because this is the equation of a circle. So let's go ahead, draw a circle.